Well, we're just about there. Welcome back, everyone, so far. I say this a lot, but this is the hardest thing about class, just watching that clock tick down till we can start.
Is it okay if I submit the homework a little late since I didn't realize it was due at 1 o'clock?
Yeah, that'd be just fine. No worries.
I'm used to things being due at 11:59, not 1 o'clock.
Yeah, I hear you. Well, it looks like we can start officially. Welcome back, everyone. And yeah, thanks for mentioning that. As far as the due dates go, I had to put a time into Canvas just because it wanted one. And it just sort of auto defaults to the time the class starts, but I'm not specific on when you turn it in. So if you're in the in-person section and you just forgot to turn it in, you could always scan it, send it in later after class. And same for the online section. If it comes in at any point today, section 2.2, it'll be considered on time. Well, welcome back. I have kind of a smattering of announcements so far on the Canvas page. We're in section 2.4. And next week on Tuesday, we'll be having our first exam that goes up to that section, 2.4. But before we start going through the announcements, any questions or other further comments so far? David asks, when do we need to take exam one by? Exam one is officially considered to be on Tuesday. You can schedule it at any point on Tuesday that you'd like, and that would work out just fine. So work with the testing center for their available time slots, work around your schedule. I think what makes a lot of sense is just schedule it for 1 o'clock, the time you would ordinarily have class. But if there's any kind of issues, if the testing center fills up, you can schedule it for any times that make sense. And that's another reason why we don't have class on Tuesday as well, since it's sensible to schedule the exam for Tuesday. And the in-person section will be in this classroom taking the exam as well, so I couldn't do a Zoom class at the same time. But there's more to that question as well that I could answer as that goes along with it. This kind of class is sort of complicated to run as far as exams go because there's lots of setup, there's lots of correspondence between testing centers, students, getting everything organized. And just to make things work with the testing centers, they do ask for flexibility in the scheduling. For example, the Pocatello Testing Center could just outright fill up on Tuesday, right as you're trying to schedule that Tuesday exam. It's absolutely possible. So I make the exam actually open on a range of times. Exam one could be scheduled from February 2nd. So some people want to take it early, and if you wanted to, then that's up to you. You're welcome to do so. It can be scheduled up to Thursday, so it's open for these entire 4 days. And that does cause kind of a fairness issue that no one's ever complained about before running this kind of class, but I am pretty aware of it. So even if you are in the in-person section, you might notice the online section has flexibility from the 2nd to the 5th on scheduling exams. So I extend the same flexibility to even people in the in-person section. Our official date, I'll be here in this classroom to take the exam, is the 3rd. But if something happens with your schedule, if you want to take it, say, early, or maybe on the 4th and the 5th, I'll extend the same courtesy to even the in-person section. I'll probably be sending it to, say, the Idaho Falls Testing Center, and just let me know as soon as possible so I can get that all set up for you. Does that make sense so far with as far as exam scheduling goes? Okay, so one thing I did at the Monday of this week was I went into the Canvas inbox system here, and I essentially just contacted every single person in the class. So if you indicate you want to test in Idaho Falls, I sent the instructions and a calendar for scheduling that exam. If you indicated you wanted to test in Pocatello, I did the same, but sent you the calendar for the Pocatello Testing Center. So try to get that exam scheduled as soon as possible, just to make sure you have your preferred time, because again, slots and days even can fill up sometimes on these testing centers. And if you don't see the instructions through Canvas, whenever I send a message through Canvas, it also bounces a message to your ISU email address. But if you're still not finding it, just send me a direct message right away, either through Canvas or say Gmail with your ISU account, and I'll send you those instructions for scheduling the exam. I'll probably write an announcement here so you can check any announcements, even if you join the class late. I'll write an announcement here just as another reminder, probably on Thursday and Friday or Friday for scheduling the exam. But again, there's lots going on for a class like this one. Any further questions so far, folks, about exam scheduling? Okay, well, as far as the exam content goes, we see it's going to be these three sections in particular. And I'm a big fan of parallelization. So whenever I go to write the homework exercises, we'll assign them. I base my lecture notes, these notes you see up here, on those homework exercises. And when I go to actually write the exam, I base my exam on both sets of materials. So really, I would say a great order of operations for studying for any exam in this class is absolutely get caught up on the homework. It's worth quite a lot in this class anyway, so that's a good way to just have a best practice. And as you're doing these kind of problems, just think of them as they're real exam questions in a certain sense. Sure, the exam questions will be different, but this will be already great preparation for your exam. Try to get them solved as soon as possible, and I'll be working, getting caught up on grading these sets and sending it back to you ahead of the actual next week number 4. Well, I think I had other comments about that so far. What was it? Oh yeah, as far as due dates go in this class, I don't in fact have a late policy. So even if you're, say, a couple days behind on 2.2 or section 2.3 that's due Thursday, get them into me as soon as possible, and I'll make every effort to have them graded and returned to you before February 3rd, the day of the exam. My schedule on Monday is pretty tight, so if it gets sent on Monday, it's going to be hit or miss. But if you send it to me on Sunday, say anytime before 5 p.m., I have a good opportunity to get everything graded and sent back to you for extra feedback to help with the exams. And aside from that, other things to discuss about the exam is they're closed book and closed notes, but you can have a scientific calculator that you provide yourself on the exam. The testing centers typically don't provide these, so just use a calculator you're used to using on your homework, and a basic scientific calculator will do the job. That was supposed to say graphing. I'll fix that later on. Graphing calculators are not allowed, so things like the TI-84, other calculators that say CAS for computer algebra systems aren't allowed, but something like this will do the job. Other things to mention, again, sorry for the lot of announcements today, but it's a lot to talk about in the first exam. There's other materials provided here to assist with studying, and this exam 1 formula sheet, here's what it looks like, will be the last page of the real exam 1. So it's good to have this pulled up when you're studying for the exam, just to familiarize yourself with the information and tools that's available to you. And it also will inform you on what kind of things aren't provided, what kind of stuff do we have to have memorized, not on this list. Other materials are 2 sample exam questions, version 1, version 2. Version 1 is really just the lecture notes, but converted into kind of a worksheet format where there's no formulas or comments distracting you, so just a problem by problem set. Version 2, this is just a set of new problems on a section by section basis. So if you're all caught up on the homework assignments, 2.3 through 2.4, these would be just additional problems you could take a look at for further practice. And essentially on every single exam, it's going to just be a repeat of this entire block you see here. Different sections, different notes, but the same kind of organization. I think I ran out of things to say finally, but any questions at the moment, folks, about exam 1 or otherwise? Okay, we'll get that exam 1 scheduled as soon as possible. If you're missing the instructions or just have further questions, don't hesitate to reach out to me at any point. I'll be very happy to help out. So our goal today is to get through section 2.4. That's going to cut off the content on exam 1. Since I don't want to try to rush through 2.5 if I wrote an exam that involved it, I try to end it a little bit faster so you also have extra time to actually work this assignment, get a chance to turn it in early if you choose to do so for extra practice and getting feedback on that exam. So last section we just finished was sets, unordered collections of objects, elements, possibly numbers or otherwise. Now, section 2.4 has a lot going on, sequences, vectors, and matrices. It's kind of a lighter section, but there is some interesting material in there. And just for a quick way to think about sets versus sequences, we're indicating we're dealing with a sequence if order suddenly does matter. We allow duplications, so it's a different kind of structure that we'll be looking into starting in 2.4. So let's turn to those notes. There's a revision here because I found when I was proofreading this morning, one unfortunate error right here at the very bottom. I think I indexed this with I equals 1 through M. That's a humongous mistake. So sorry about that distraction right there. Kind of reminds me of the typo with the change of base formula logarithms. I'll try to catch these a little bit sooner before I actually post the notes. The index has to be a K, so that's the one revision on the notes. Aside from that, here's where we'll start. Sequence will be considered an ordered collection of objects, which we will call elements, components, or typically things like entries are a great way to talk about them. They are typically indexed on the numbers 2, 3, 4 through N. Or excuse me, I'm misreading my own definition. When the number of elements in the sequence contains just say 2, 3, or 4 elements, we call them an ordered pair, triple, or an n-tuple respectively. And sequence is a big word here. We're looking into just finite sequences up to n elements. Calculus 2 deals with sequences of infinite length, but the notes are really going to be contained to these kind of objects. So think finite length for all the sequences. And just for a really fast example, here's a 5-tuple sequence. This is the network connection transmission control protocol, or TCP connection. And this is what it looks like. It's kind of hard to see because we have to really focus on those commas separating out the components of this particular sequence. So the first thing will be, I'm going to see my notes here since I'm no expert on this. So if you have extra insight on anything I say, don't hesitate to chime in. But this will be the source IP address. So say your computer, destination IP address. And this will be the port. As I understand it, that's like a process for how your machine is sending data. This is the outgoing port. This is the incoming port. And from what I did a quick Google search, 80 typically means this is an unencrypted connection. So maybe a dubious website potentially. Hopefully it's not a bank. And TCP is just the instruction set for how all of this information is handled. So here, order is now extremely fundamental because if we change around any of the components, close that, in this particular sequence, the communication is just not going to work as expected, probably won't work at all. And the other example of sequences, again in Calculus 2, are objects that have infinite length. Well, that's our first definition so far. We're going to launch into an immediate use for sequence in the Cartesian product. But any questions or examples at the moment with the initial definition? Okay, so the immediate thing we're doing right away is taking a sequence, we can enclose it with brackets like that. That's typically how we might write, say, an element in Calculus 3, for example, thinking of a vector, a special kind of sequence. Or they could be parentheses if it's just more natural to write that way. But going with that definition, here's our new object. The Cartesian product between two sets, as we just studied them in section 2.3, is indicated this way. It's a product, so we use a multiplication symbol, although this is not the definition we would use in any arithmetic sense. A cross B as our Cartesian product means a set of sequences containing just 2 elements. If there was 3 sets here, it would be an ordered triple instead of an ordered pair. We see AB. The only requirement is that the first element has to come from the set A, and the second element has to come from the set B. Order is not important, so if we change that order, we're not looking at a true element inside of this cross product. And cross products are just a natural thing we study really all the time. Say, way back into high school algebra, we might not have used that symbol when we were working in the Cartesian plane, but R2 can be defined as R cross R, where we're looking at this either as parenthesis, a typical ordered pair, or bracket in the definition. This is a ordered pair, a sequence of two elements, where here both A and B happen to be real numbers. Linear algebra studies things like R2, R4, and so on, and this is just our way to relate that back to the new definition, Cartesian product. And a pretty fast example on this is the language SQL, structured query language. It has an object that's essentially completely analysis to the cross product. It says here, a Cartesian product in this language, SQL, is used for cross joins where two tables are combined to produce all possible pairs of rows. So a really fast example is if the set A is a customer list, so all possible customers, maybe this is Amazon.com, so this is a fantastically huge database on its own. If B is a set of all products, then A cross B will be all possible customer and product pairs. You can imagine that is an extremely big and wild structure, but a way to think about this is A cross B in this situation would just be the maximum set of all pairings between A and B before any filters are applied. So although it's an interesting set, oftentimes we do want to pare it down to make it more manageable, but this will be the role A cross B would play in that kind of language. Mateo says, is it kind of like matrices? Not quite just yet, matrices on these. This one's a little bit different where it's really just going to be a collection of pairs of objects, whereas matrices would be something more along these lines, kind of like an array where we have, thinking in terms of sequences or vectors, we're combining three different vectors or sequences together to make one new structure, the matrix. We'll look at finite sized matrices, but these could also, just like sequences, be of infinite size. Other questions at the moment? Sorry, figure out where to scroll to. Okay, so think of a sequence as a finite collection where order does matter. Then the Cartesian product, the first really big object we'll study in these notes, is a sequence of size however many sets you're taking the cross product of. So if there's three, this would be a triple instead of a ordered pair. And the elements that go inside the cross product correspond to the sets that you wrote out. So if you go A cross B, you take elements from the set A, elements from the set B, and we're looking into all possible pairings whatsoever. So this could be a pretty large set, but if we're doing these by hand to study them, I'm not going to try to write out things you have to write down 20 different elements for. So to practice this immediately, we'll take a look into the cross product of some basic sets, just see how it goes. So find the Cartesian product of these two sets. They're both of finite size. And when you have finite size sets, there's also a nice formula you could tie together from the last section notes. If we're going to write out a set that contains all possible pairings, ordered pairs, it's good to know how many objects are inside that set. So we can say the cardinality of A cross B has a really satisfying formula. It's the cardinality of A times the cardinality of B, or the size of the set A times the size of the set B. A has size 2, 2 elements. B has size 3. So it tells us all possible pairings between these two sets. That's the cardinality of A cross B. We're just going to list out 6 elements. That's nice to have that number, just in case we missed something. And finally, writing this all out, let's kind of color code it slightly differently. Let me try again with that. Green, there we go. If we write out A cross B, what we'll produce for this is a set of ordered pairs because there's just two sets in the cross product. Following the notation as it's defined in the book, I'll use the angle brackets, but I would say that's more of a stylistic choice. In some contexts, parentheses would make sense. And so if you prefer to go that route, I won't be too picky. But it is a set of elements, so we should start by writing down the set symbol. Then just start writing out the listings inside the set X. Excuse me, set A. The element X will be paired with the element 1 from the set B. Next possible pairing, I'm going to stay with this element X and think of it as essentially distributing across that set B. So X can also pair with the element 2 from the set B. It can pair with the element 3 from the set B. And we're halfway there. We're going for 6 elements. Sometimes being organized really helps out so that we know what we have all the information there. The next set of possible pairings involve the first element Y from the set A. So go Y, comma 1 to pair it with the element 1 from B, and so on down the line. Essentially, all I'm doing is flipping the first component here in every one of these sequences to a Y value and duplicating the second component from the set B. So this lists them all out in a kind of an orderly way. Now we are writing down a set, so the order here is irrelevant. But again, if you write it out in kind of a logical way, it's a great way in your mind to check if you've got everything that you're expecting to get. 6 elements in total. So that's the final element. We'll put a curly brace here to close the set. And that's the whole punchline to A cross B. Again, it's useful in a lot of different ways. R2 defines a vector space, all ordered pairs in the Cartesian plane. But for the moment, it feels like kind of an abstract novelty. We'll see a lot of different kind of uses for this. In fact, one thing that's kind of strange in a certain sense is if you think about the original definition of a function, whether you're thinking, say, the vertical line test type of definition, or the unique output for each input definition, you can get really pedantic when you define functions, and in the most precise way possible, a function involves a cross product. So we'll delve into that when we get into the next section. But any questions so far, folks? Just practicing the definition in this example. Okay, let's try out another one for just the sake of practice at this point. Here's the next 2 sets. Here we have a set 1, 2, and the power set of A immediately next. So really this one just becomes a review problem altogether. One thing we can do is, once again, analyze the size of the cross product we're expecting to find. So if we write out that information, the size of A cross the power set of A, we can first factor in this way. This will just be the size of A multiplied by the size of the power set of A. The cardinality, or the size of A, is just 2. We have 2 elements inside that set. And here's one nice formula. When it comes up the topic of the cardinality of a power set, if A is a finite set, this is just 2 to the power of the cardinality of A. So that's the topic we looked into at the very end of the 2.3 notes. So this turns into 2 times 2 to the power, we know the cardinality of A is 2. And that tells us altogether we're expecting to find 8 elements in the cross product between these 2 sets. They're going to look a little funny, but this was just a reminder that the set can contain anything as long, well, it can contain anything whatsoever, and we can talk about the cross product between them. So let's start off with set A, set B, thought of in this way. Let's first just compute the power set of A. The power set of A is the set of all subsets. And so the first fundamental thing that's weird is the empty set is in fact a subset of A itself. So we have to throw that in. Then the next smallest sets after the empty set contain just one element, singleton sets, you could call them. So there'll be 1, 2, And the last largest set after that is the entire set A. So let's write that in. Or you could have wrote it as curly brace 1, 2. But letting the variable name A stand for it is just a nice way to write that kind of set. So that's where, hang on, yeah, that's right. That's where the number 4 comes into play from right here. Confuse my own self looking at that note there. So this value here is the 4 elements that we're seeing in the power set of A. Now we're ready for the cross product. We can write out A cross B. Well, rather A cross the power set of A as a set of all possible pairings between that set A and the power set. It looks a little funny, but here's the listing. 8 objects altogether. So starting with element 1 from the set A, I'm going to think of that 1 as essentially pairing over to all these possible second elements, starting with the empty set. So that's the next element in the cross product. Then we just go down the line. 1 and the set that contains 1. We know from our work on sets in the last section that although this looks kind of funny, it is important to write the curly brace around that, or it's not the same object. So if we call this 1, 1, that's not an element that actually belongs to the cross product. The second component is always a set, in other words. Then at this point, once we see how the pattern goes for any cross product, it just becomes a kind of a matter of how fast can you write? We're not going to try to race through it, but really we're just going down the line, putting it down these elements. So pair 1 with the set that contains just 2. Next, pair 1 with a set that contains both 1 and 2, or you could just write A if you prefer. I'll leave that up to you, how you'd like to format that. We need 4 more elements that will have the total listing of elements 8. But really it's just a matter of flipping the first element 1 now to a 2. There was, say, 5 elements here. This would be a really, really big set. So as far as the homework goes and the exams, I'm not going to make you write forever. Some of them can get a little bit long, so be organized. But in exams, nothing too major, so we are not writing forever. So all we're doing is changing the first component to 2 on these. And now it's just a matter of really copying, right? We're going to use those same second components, those 4 different kinds of sets. So we go 2 in the empty set. Organization here just makes it become more of a copy down what you see above, making sure your first component is 2. 2 in the set that contains 1. 2 in the set that contains 2. Feels the same, but logically they are different. My curly braces seem to get worse and worse the more I draw them, so let me try to slow down with them. Next is 2 in the set that contains A. And then finally, there it is. The Cartesian product is a set containing all possible pairings, and we listed all 8 of them. Well, any questions, folks, with Cartesian products at the moment? Okay, I felt like we should do one more just for the sake of practice, because part B was really just a review of what a power set is fundamentally, and being very careful with our notation, making sure we write down a set as a second component. But it's really like part A, that's just a cross product between 2 sets. But we can have a cross product between any finite number of sets that we would like. So here is our next example. The analogy is, if you're working in 3-dimensional space, physicists love this setting, R3, you're really just fundamentally looking at R cross R cross R. If you wrote out this as a set, you just mean A, B, C, such that A is an element of R, B is an element of R, C is an element of R. We could have certainly abbreviated that. A, comma, B, comma, C are elements of R. But here I just want to emphasize if we change one of these sets, we can still have the same definition. You just have to make that change on those particular corresponding components. So here's the analogy here with finite numbers of elements. Color coding doesn't really work at this point, so we'll just be very careful as we go. If we take A cross C cross D, maybe the first question we want to ask and answer is, what is the cardinality of this set? Anyone happen to know the number of elements in that three-way cross product? Yeah, absolutely. We would take 2 elements here times 2 for 4 times 2 for 8, really just following the logic of these same formulas above. So we're dealing with 8 elements on this one. We could imagine it might be more interesting if we put, say, 10 elements in C, but then we would be here for quite some time. We'd have to list out 40 entries altogether. And I feel like that's more busy work than really understanding the cross product. So I kept the size of the sets kind of tame, just to emphasize the idea of what they really represent when we go to write them out. So now A cross B, let me try again. For no reason in particular, I skipped the letter B. A cross C cross D are now going to be ordered triples. So we're going to have elements that look like this. I'm going to organize in this kind of way. Start with the element A here, the element 4, and then vary on 3, 5. So let me write out A, 4, 3, A, 4, 5. Then we can flip this one over, go A7, and then vary on the 3, 5 here. So that'll give us 1 row of 4 entries. We'd be halfway done. So A7, 3, A7, 5. There's more, but now at this point, all we're really doing is copying what we saw above, but changing the the very first component to the second element, B, in that set A. So really the same stuff, just vary the first component to a B. So B43, B45, B73, and finally, B75. And that's our full set, the entire cross product. We have 8 elements altogether. So as long as we didn't duplicate anything on accident, we have the whole cross product listed out. Well, any questions at all, folks, so far with this topic? Okay. Well, this section again has kind of a random smattering of topics going all together. They're all logically connected with the idea of sequences, which define the cross product. Now we're going to move on to other topics, vectors and matrices of other order collections. And this is the part of the class where if you have taken linear algebra, it's kind of a short review. We're not doing anything too major when we think of a vector. But reading the definition kind of is mysterious in a certain sense. We're told a vector is a sequence coming from a set Rn. So Rn is a cross product. When we see that, we just mean Rn is R cross R cross R, where this is repeated n times. So we think of a sequence as, or excuse me, a vector as a sequence x and Rn for some positive integer n. Typically, we're thinking 2 or higher. And for every vector x and Rn, we can write out its components as xi to denote the ith component of the vector x. And this is a pretty important question, I would say, to answer. What makes a difference between a vector and a sequence? They can be listed out as the sequence we were looking at as the very first definition. But really the idea is it's all about connotation. If you say the word vector, it means that there is an extra operation going on in the set Rn. Rn would be considered now a vector space. So we're not just thinking of the ordinary, say, plane if it was R2, or three-dimensional space if it was R3. We're thinking there's a vector space in action, which means we're doing stuff with these vectors. There's a way to add them together. So that's the connection. If you say you have a vector, you're probably going to be able to add them with whatever the operation defined happens to be, and you'll have a way to multiply. Here, we'll have a sum. Sometimes this is referred to as vector addition. We'll have a product, and sometimes this is referred to as scalar multiplication, if you have something called a vector. So really, that's all that's going on. There's extra connotation if you say vector as opposed to sequence. Well, for the really fast example, physicists like R3, three-dimensional space, but that's really not good enough for them if they want to discuss other interesting things going on in physics. They move over to R4. They're going to work in a structure called space-time, and it would look like this. It's a four-tuple. X1, X2, X3 would refer to three-dimensional space, and X0 would be the time variable. It's often defined as a value c times t, where c represents the speed of light in a vacuum. So that's an interesting object, but physicists want to do more than just deal with that sequence. They put operations on it, vector addition, scalar multiplications, and so now it's called a vector in that sense. So that's the next topic, vector, which goes into matrices that we'll be looking into next. But any questions or comments with the first initial definition? Okay, well, we won't do too much in this section as far as linear algebra goes, because again, this is not meant to be a linear algebra class. And chapter 2 is really just meant to collect some topics that will be useful later in the book. So a couple things we'll look into as far as vectors go are the length of a vector. We'll write it out this way. Sometimes that's referred to as the norm of the vector, so that'll be a synonym. And it's the square root of the sum of the components squared. So our summation notation from the first section of the book makes a comeback. Xi squared just means go to every one of those components, square them, add them together, taking the square root, and now you have the length of that vector. There'll be a unit vector if the length is 1. And other fun things we can do is add together the vectors. But this is done component-wise through this definition. You'll add the first component of x to the first component, of y. And this is what it's meant, the way it will be defined. Zi will be the sum. So that's the vector z after adding the two together. Take the ith component of x plus the ith component of y and just add them together. When we refer to scalar product, we'll write out as a times x. The notation here says the product z equals a times x will just give us components zi, where you just multiply every component by that scalar a. And finally, the dot product is really kind of hidden here. This is x dot x. The dot product just says, take the corresponding components of both your vector x, your vector y, multiply them, and sum all of the multiplied components. So that's a pretty big rundown of definitions if you haven't seen these things ever before. So we'll treat these kind of carefully, go through these instructions in a very precise way for each one of these 3 vectors. But any questions or comments at the moment with these vector operations? Okay, so once again, we're still dealing with sequences. If you call these a sequence, that's okay, but calling it a vector just tells us you have this extra operation in the background, things that you can do to operate on the vectors. So I shouldn't scroll too far past that. Here's a set of 3 different vectors, a, b, and c. They're both in the space R2, because every one of these vectors have 2 components. And just to go down the line, the definitions, we'll find the length. We'll do what's so-called linear combination, and then combine that with a dot product of a vector, find the length of that one as well. So down the line, the length of the vector b we cite the definition here. It says take the square root of the components squared. So we go to that vector b, square the components, and take the sum. That means this will be the square root of 9 plus 25, resulting in the square root of 34, and the operation's complete right at that step. And geometrically, we really did something. We're calling it a length, and we really mean that depending on the vector space we're working on. Here, if we drew out a sketch and plotted the vector b, -3 is the first component, so 3 units in that direction. -5 is the second component, so 5 units down. And we can visualize this vector b in a number of different ways. We can think of it as a position vector in the sense that there's an arrow, if you decide to think of it geometrically, that could go from the origin to B. Or we can think of it as just a singular point in R2 with coordinates -3, -5. Well, either way we visualize this, when we found the length of the vector B, we were just finding the length from this point here all the way to the 0 vector, the origin. And that's the length of B. Square root 34 is the distance from here to here in R2. Well, any last questions, folks, on that operation here? Okay, again, nothing too major. We just have to know how do the definitions work when we're doing these kind of problems. And the exercise will reinforce some of these exercises. So again, it's kind of a weird topic if you've taken linear algebra, as I've meant a few times. So think of this as just kind of a relaxing set of material, just brushing up on the definitions. Next thing I'm hinted at before is often called a linear combination. A word you'll hear over and over again if you take a linear algebra class. Linear combination just means you're taking a set of vectors, you're scaling them. 2 times a is a scalar multiplication, and you're also doing vector additions at the same time. You're adding the opposite of b, adding 4 times c, a scaled version of c. So we'll run through both vector addition, the sum we see here, and the scalar product definition here as well. To start out, 2 times a is just scaling the vector a, and the definition says you go to every single component and just multiply by that scalar a. So whatever that happens to be, multiply by that, hang on, let me fix that highlighting, multiply by that value. On a, we're scaling by the scalar 2, so this will turn into 2a. On the vector b, we're rescaling it by the scalar -1, so multiply both components by -1 for 3, 5. And here we're rescaling the vector c by 4, so this becomes 0, 4. And that does all of the scalar products, all of the scalar multiplications said differently. Next is the vector additions, the sum, but we just do these component-wise. So add the first components all together, and that's the new first component of the sum. We'll get a 5 out. Let me know if my numbers go sideways at any point. The second components are going to be 8 plus 5 for 13 plus 4 for 17. And that's the resulting vector from this linear combination. So any kind of linear combination like this is always just going to produce another vector. Well, any questions, folks, with that operation there? Okay, next one is just going to run through the dot product. And there's a lot of stuff we could say about the dot product. If you were, say, taking a Calculus 3 course, or if you've already taken one, this is about where your first chapter would start. And if you were going to take a linear algebra class or you've taken one, this is usually where the last chapter would start in the textbook you're working with. Dot product allows us to do lots of things geometrically, but here we're just going to see how the operation goes with a fast practice problem like this one. So dot product says you're taking a new sum. the ith component of the first vector times the ith component of the second vector, do all those pairwise multiplications, and then add them up. So in this object, we're taking A times C, multiplying B. Let's start off by just doing this operation first, the dot product. A dot C, sometimes called the inner product if you prefer to think of it that way, would be taking the first component, 1, times the other first component, -3, add to it through the summation symbol. Now we're updating the index, which is a 1, to an index of 2, but that just means take the second component of 4, multiply it by the corresponding, the corresponding second component. Looks like I made an error on that. That says A dot C, and I did write it there correctly, but let's make sure my eyes don't deceive myself. C is not -3, -5, so let's backtrack a little bit. Sometimes color coding helps me quite a lot to make sure I'm looking at just the right vector, and there's a listing of them. So starting over, A dot C means take the first component, 1, multiply by the corresponding first component, 0, of the correct vector, C this time, 1 dot times 0 plus, do the same thing with the second component, 4 times 1, and then that would just come out as a 4 altogether. So we want the length of A dot C, rescaling the vector 4, and we're pretty much just about there. We can now write with this operation, the length of A dot C, scaling B, is 4 times B. Any questions so far, folks? Just running through the dot product side of the operation. Okay, at this point, really it's kind of up to you how you'd like to compute this. You could take 4 times B, you'd get a vector -12, -20. You would square the components just like you did on this operation, then take the square root of the result. It'll be a fairly big size number, and that square root will reduce. But if you want to just get right into the reduced answer, here's another operation you can take. A scalar multiplying a vector in this configuration can come out in this way, take the absolute value of whatever the scalar is, multiply it by the length of that vector B. And that's kind of handy for us because we've computed the length of that vector B already. And so this would tell us, doing it as fast as possible, you would get a 4 times the square root of 34. If you did it the other way, take 4 times these components and then square and add together those components, it works out too. Just a little bit more work simplifying the square root. Well, that's our rundown for vector operations at the moment. Any questions at the moment, folks, getting through these? Okay, well, the next topic we'll look into to finish off this section, again, it's kind of a light section compared to what we've done so far this semester, is look into matrices. The dot product does make a comeback at the very end of the notes when we're doing some matrix multiplication, but for the moment, it looks like it's kind of an oddity. We didn't say too much about what happens with it geometrically. That's one of those things that are of really huge humongous importance when it comes to these kind of vectors. But the next objects we'll study, let's put a border here, will be matrices. So an n by m matrix, M, we'll think of this as a two-dimensional table of real numbers containing n rows and m columns. We can index every entry as an ij entry to refer to the entry in the ith row, jth column. And if we want to give that entry a name, we might call it M that came from the matrix M originally, ij, so ith row, jth column. Think of rows as things going horizontally, columns as things going vertically. If you keep those two directions clear in your mind, you're all set for matrices. So such a matrix M, if we define it, as an element of this space, Rn times M. So this is an interesting space altogether. and we refer to M as having size n by M. So if we write down just a random matrix to think about these, let's say M looks like this: 1, 4, 5, 3, 6, 2. Let's put down another matrix N just to compare. Let's say N goes this way: 1, 1, 8, 7, 4, 3, 6, 2, 1, just random numbers. I like positive numbers, so let's throw in a negative because we can. So here's two particular kinds of matrices altogether. When we analyze these, again, think of these horizontal sequences of numbers as being the rows. So this would have 2 rows, 3 columns. And to abbreviate that, we often just write down a quick statement. This is a 2 by 3 matrix. So we say it comes out of R 2 by 3, meaning it would have R2, R2, R2 for columns, but 3 columns altogether is the times 3 that would go here. So M is in R2 by 3. Likewise for N, this one has 3 rows altogether. Let's use the shorthand. So 3 rows, it has 1, 2, 3, 4 columns. So it's a 3 by 4 matrix. And once again, think of this as the number of columns. 4 of them. This is the number of rows. So 3 rows. So that's 2 random matrices altogether. And as far as the notation goes, if you say M, let's write down an actual subscript to that. I'm thinking of this part of the notation. If I write down M2, 3, comma is a good idea, especially if you have, let's say, lots and lots of rows. So we're separating this out. M2, 3 means go to the second row, so somewhere in here. Beyond the 2, after the comma, 3 says go to that component, a 2. So that is the 2, 3 component, just the scalar 2 itself. Well, I think that kind of conveys all the notation so far at the moment. Really, we're just building our structures into something larger. A sequence was an ordered listing of numbers. We think of a vector as being the same kind of object, but it has extra operations: vector addition, scalar multiplication. And all the matrix is doing is putting vectors together. Whether you're thinking in terms of rows versus columns, we have vectors put together to build out the matrix. Well, the next interesting matrix is going to be the identity matrix, but any questions or comments at the moment? Let me hide some of that for the moment. Let's discuss next the identity matrix. It says the n by n identity matrix. Now it's good to pause right there. N by n is telling us it will have n columns and n rows, and that's a requirement. N is duplicated here, which means this has to be a square matrix. Same number of rows and the same number of columns. Often indicated just as I, kind of thinking that like the number 1 in Rn by n. And it satisfies this interesting statement. The ijth component of the identity matrix is either a 1 or a 0. It's a 1 if the row equals a column. Row being the same as the column means you're on a diagonal. It'll be 0 otherwise. So if we write down a couple identity matrices, say I2, here we're being specific if we put a subscript 2 there, that this is from R2 by 2. So I2 would be a matrix that goes like this. This is the 1, 1 component. We're in row 1, column 1. So the subscripts match, we put in a 0. This is going to be the 2, 1 component. We're in row 2, column 1. That's a mismatch on those subscripts, so we would put a 0 down here. Likewise, this is row 1, column 2, the 1, 2 component, so it's 0. But this is in row 2, column 2, the 2, 2 component, so we'll put in a 1 there. So that's all this equation is really trying to say. Kind of an abstract way of phrasing this. The punchline is you have a 1 on the main diagonal of a square matrix and zeros otherwise. So if you wrote out, say, I4, it's a larger matrix, we would have a 1 here, 0, 0, 0, then go 0, 1, 0, 0, 0, 0, 1, 0, and finally 0, 0, 1 gives us I4. So that's a lot of notation altogether just to define matrices. But these kinds of notations are pretty standard from course to course, linear algebra, and even in this textbook. So it pays to spend some time looking into these things. Last thing we'll look into is, well, not last, but we're getting there. The last topic for this page here is going to be matrix addition and scalar multiplication. And kind of the fun thing about this is, if you see how our linear combination went above here, it's going to be really the same kind of thing. Imagine A is a matrix. 2 times A just means double every component of that matrix A. And if these are both matrices of the same size, we'll do the same thing we did here. Add or subtract the corresponding components. So matrix addition, scalar multiplication goes really the same kind of way. Saying it precisely, though, is kind of an exercise in and of itself in reading mathematical textbooks. It says, given M and R n by M. So we have a matrix with n rows and n columns, and a real number A and R, sometimes referred to as a scalar. A times M is a new matrix N, where the ijth component is just A times the corresponding ij component of the original matrix M. So that's a complicated way of saying, to do that, multiply all the entries of your matrix M by the number A. And same corresponding definition. If you're adding 2 matrices, M and M prime, you'll get a new matrix N, have the same exact size. And this is just telling us, go to the ijth component of M, ijth component of M prime, add them together, and that's the ijth component of the original, the sum N. So pretty difficult definitions to track. We have to spend some time here to really peel back what it's trying to say. Sometimes that's worth our effort because when we look into matrix multiplication, that's a complicated definition as well. But if we see what it's saying without typos, so again, sorry for that typo there, this is saying quite a lot, exactly how to multiply 2 matrices. Well, let's give these operations a try. We have 3 different matrices of various sizes. Let's maybe put this on the next page to fit it all. And just a few fast operations. Again, this should feel just about like what we were doing when we were dealing with just, say, vectors, A, B, and C from R2. Only difference is these are more like arrays now instead of just a listing of numbers. It's a list of lists of numbers. So with 3 matrices defined, we'll evaluate each one if possible. And if we get undefined, we'll mention it. The first one's not too bad. It says -5 times I, but that's context sensitive. You have to know how big is that identity matrix I. Here it's saying it's of size 3 by 3. So that means if you take -5 times I, you're just taking -5 times 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then all of this information was trying to say is multiply all the components by -5. That means the zeros are kind of friendly here. You would just get -5, 0, 0, 0, -5, 0, and 0, 0, -5. At that point, our work is done. And this might look like deja vu in a certain sense. This is practically the same sort of problem we saw on the prior exercise with vectors. But any questions so far, folks, on getting through that example? Okay, well, we have matrices A, B. They're both of size 3 by 3. We have a matrix -5A, but we have a 3 by 3 matrix here. That tells us this addition will work out. And the punchline is, if you're trying to get the 1, 1 component in row 1, column 1, all you do is go to that component, let me actually do it in order. Go to the corresponding component here in A, go to this corresponding component here in B. For negative 5i, which we computed, take that component and just directly add all of them together. So that would give us a value, -4. That's essentially the name of the game. We just have to be really, really careful that we don't add anything together. Sophia says, so the identity matrix is just all the leading coefficients in place. Depends on how you mean. The identity matrix, this one right here, would just mean you have a 1, 1, 1 across the main diagonal, and then everything else would have to be zeros altogether. Does that make sense there about the identity matrix? Awesome, yeah, so that's absolutely right. So if we said this was I in R 2 by 2, I in R 2 by 2, all we would really mean is I equals 1, 0, 0, 1. And often I like to be kind of specific when I write down the identity matrix, unless the context is crystal clear. I like to write this way, I sub 2, just to say it's of this size altogether. Awesome. Thanks for asking about that. Other questions at the moment? Okay. Well, you know, the downside for this kind of linear combination, where the objects are vectors instead of, matrices instead of vectors, is we have, well, 8 more components to go. So let me know if I grab the wrong component. We're taking 1 plus 0 plus 0, so a component of 1. I'll fill this out going column-wise. Then 3 minus 2 for a 1, plus a 0. Now move over to the second column. So I'm going down the line here. Take 3 plus 5 for an 8. Love those zeros. That's just an 8 then. Then here it's going to be 5 plus 4 for a 9. Minus 5 for a 4. Then adding these components, 2 plus 3 for a 5, plus 0. So 8, 4, 5 in our second column. And almost there. So -4 plus 11 for a 7, plus 0 gives us 7 altogether. Again, we're just going down the line for the the matrices as they are defined. For these components, the 2, 3 components, it'll be 0 minus 3 plus 0 for a -3. And last, take 7 plus 0 minus 5 for a +2. So essentially all we've done is we added A and B together, and then we subtracted 5 from the main diagonal to get this result all in one. So that's the result of adding together, those matrices. Well, this one down below is a little bit different. It says take 3 times C. Here's the matrix C, so that means this one is of size 3, because it has 3 rows going this way. So 3 by 2, because now it has 2 columns. 5 times B, well, we haven't done 5 times B yet, but we know we're going to get a 3 by 3 matrix. So this is of size 3 by 3. And now we have a problem on this one. This one has not enough entries to match up with all the entries in 5 times B. If we look into the definition, it says, this definition, both of your matrices, both M and the second one M prime, think of M as 3C, M prime as 5 times B, they have to come from the same space. They have to be of the same exact size. So even though it's not written here, that's a requirement. And we have never defined anything like this whatsoever. So we would just say straight out, undefined. And that's this part of the instructions. If an expression is undefined, say so, we did. Explain why. Well, this is kind of the explanation that we wrote down here. If we want to say something further, we can say dimension mismatch. Or you could say the sizes of these matrices are not the same, or there is no third column in the matrix 3C, but 5B has 3 columns. Lots of ways to say this. But either way we look at it, it's an undefined sum. Well, that's the entire landscape of Matrix addition, scalar multiplication. Again, it kind of loops back to what we were doing with the vector addition and scalar multiplication of vectors. Any last questions or comments before we take a look into the last topic? Okay, last topic is kind of tricky just to start out. These aren't so bad because we're adding together corresponding components or just rescaling an entire matrix like the -5i. But when it comes to matrix multiplication, it seems like it's a whole new kind of landscape you're looking into out of nowhere. The definition looks complicated, so let's walk through this really carefully. It says we have taking a product, A times B, of two matrices where A is of size n by m, the matrix B is of size m by p. So this means A has n rows, but m columns. This is saying B has m columns and p rows. And this part here is required. Much like adding matrices together, we had to make sure that we had the right number of components in both matrices. Here, the requirement to actually define A times B is these two dimensions have to match. So these must be equal. The definition doesn't make a big deal out of it, so these are tough definitions to read. It's kind of easy to miss what's important when you see these at first, but that's a big deal. If those numbers differ, we say the product is undefined and the whole operation stops. But if they are defined, we get a new matrix M. It's of size n by p, where these came from specific places too. The n was the number of rows in the original matrix A. The p was the number of columns in the second matrix B. And so another thing that's unwritten here is the order does matter. Matrix multiplication is non-commutative, so A times B is not necessarily the same as B times A. They may not even be the same size in the first place. Or you can have a set, A times B, that's defined, but if you change the order, B times A could be undefined. So the order we write out these matrices are fundamental and important. And the last thing is, here's the definition for the ijth component of the product M when we multiply A times B. It's kind of nasty to track, so we'll look at how this works when we do our first multiplication, A times C. But a great way to think about it is, this is a dot product of the ith row of A with the j column of B. So that's what matrix multiplication really boils down to, a series of dot products that's going to give us every single one of the entries. So there'll be n times p dot products altogether to get that kind of matrix. And just for a quick example, because I feel like doing this random linear algebra without any connection whatsoever to computer science is kind of rude. The biggest probably application going on right now is large language models. So training AI on various data sets is really fundamentally a gigantic amount of matrix multiplications. If you want to look into a little bit more on that, I have a fast video that goes here. I have another video, but I felt like one is enough. But if you're curious, I could post the next one. So this gives you an idea of what matrix multiplication could be used for as far as this topic goes. Let's take a look. I think we have enough time to try out one product, A times C, but any questions so far with the definition? Okay, let's give this a try. The very first thing you want to do in any multiplication like this of matrices is look before you leap. If this is undefined, then we are just done and we don't have to do too much. So let's look into the size of A. It's square, so it's of size 3 by 3. So 3 rows, 3 columns. We're multiplying it against a matrix C. This one has 3 columns. Excuse me, I said that incorrectly. It has 3 rows. It's always good to keep that straight in our mind. by 2 columns. So there's a match, 3 by 3 for the inner dimensions. That means we can in fact do the multiplication. So A times C, I'll write it in as 0, 1, 3, 3, 5, 2, negative 4, 0, 7, multiply by 1, 3, 0, 1, 1, 1, results in a matrix of this size. It's going to be 3 by 2. So we'll go, let me match that up a little bit better. We need 3 rows, so it'd be of that size, and just 2 columns altogether. So now I claimed this is all about a dot product. Let's see if we can walk through this definition, see how it all comes together. And writing it down like this is actually not a bad idea because there's lots of action happening with these numbers. Let's suppose we're doing the ij component, but we're here, the 1, 1 component. You would have a 1 here and a 1 here for both I and j. But what's changing is k. So we'll start in row 1. If there's a 1 where it's highlighted, k is the column, and it says k is going from 1 up to 3. You're moving across this entire row, in other words, when it says aik. So you're going that way. But then the indexes change. K is the first component, so it's saying you start at k is 1. When k is 2, you move down to the next row. When k is 3, you move down again to the third row. And you keep j fixed, which means you're always in one particular column. So in other words, you're moving down that way. So that's what the indexing is saying in this sum. You multiply the components together, add them up. But like we remarked, that's really just a dot product altogether. So take the component 0, multiply by the component 1, we'll get a 1, plus the component 3 times this component 3, so a 9, plus the component negative 4, plus that component 0 for a 0, and the output is 9. That's what directly goes inside that entry there. So 9 to start. We have several more to get through, but this is the major thing we want to explore. How does the definition work? What are we doing fundamentally when we're getting these values? And here's another way to think about it. I usually like to think in terms of building out a column because I'd like to have a definite process. And when we're building out a column, follow the highlighting. All we did is take those values, multiplied against those values, add together to get a 9. To get the second component, well, that I there changes to a 2. So you'll have a 2 here, which means you're using all of these components, but we're keeping the column frozen. So it's just a new dot product for the new entry. Oh, sorry for missing the chat. Sophia says, where did the 9 come from? Could you explain that again, please? Oh, yeah, absolutely. It's a really tricky product, so this might be a good one to come back to when we're back in class next time on Thursday. So taking another look into that one, let's think in these kind of terms here. This is telling us we're going to move across the column in row 1, and this part says j is changing as the second index here. That means you're moving down the rows. But in terms of colors, this is what it looks like. Go across this row 1, down this column 2. In other words, take 0 times 1 plus 3 times 3 plus negative 4 times 0. Let's highlight that just to see the correspondence. This comes out as a 9 altogether, thanks to the nicely strategically placed zeros. And that's where that entry of 9 came from right here. And then we have to do it 5 more times, but once we see how the pattern goes, it's not so bad. Other questions at the moment with that entry there? Yeah, you bet. Thanks for asking about that one. Again, there's lots going on with this one, and we could probably race through the arithmetic, get the 5 other entries down on paper. I think this will be a good one to come back to when we start off Thursday's class a little bit more fresh. We'll run through this again, complete the multiplication, and try out a couple more examples. And if folks would like, we could write down just another random one for extra practice. But any last questions or comments so far? Oh, didn't mean to do that. Okay, well, we're nearly done with this section 2.4. There'll be a lot of big takeaways when we go into the next section notes and the rest of the chapter. So this is material we'll return to. But unless there's any other further questions, have a good afternoon, folks. And we'll be back to this spot in the notes when we come back on Thursday's class. Take care, and I'll see you all Thursday.
Thank you.
You bet. Have a good one. Thanks. Awesome. Thanks. Yeah. Have a good day. You too.